Here's an interesting problem. We've got a situation now where we're taking the limit as x approaches 1 of 1 over natural log x minus 1 over x minus 1. The problem with this guy is that when you put 1 in for x, you get 0. That's 1 over 0. So then we have to go, well, what happens when we're getting really close to 0? And so as we get close to 1. And what happens is as we get close to 1, we get a decimal really, really close to 0. So we're dividing 1 in the first case by some decimal really, really close to 0. What this means is that the limit for that first part goes to infinity. Same rule for the second. If I put 1 in, I get 0 again. I can't do that. But if I put a number that's really close to 1 in there, I have a really small decimal and that small decimal on the bottom, again, makes us approach infinity. So I have an indeterminate form, infinity minus infinity, and we can't do this. So here's what we're going to do. We're going to use L'Hopital's rule. The problem is, right now, L'Hopital won't work because we've got these constants in the numerator. What we're going to do is we're going to combine the fractions by multiplying the top and bottom on this fraction by the natural log of x, and the top and bottom on this fraction by x minus 1. This is no different than things that you've done in the past when you've had to solve for x's. Okay, we're just putting these fractions together. But what happens is we get the limit now as x approaches 1 of x minus 1 minus the natural log of x. That's on the top. And on the bottom I have the natural log of x times x minus 1. Okay? This is a lot easier for us to work with now because now I've got a function on the top and a function on the bottom, the derivative of which shouldn't all be 0 because we've got some natural logs running around. So what we're going to do is we're going to look at these guys then, and we're going to let f of x equal x minus natural log of x minus 1. So the derivative of that is 1 minus 1 over x and then 0. Okay? So I can put him back into the numerator here, and then let's look at the next one. The next one is g of x equals x minus 1 times the natural log of x. Well, we've got a product rule, this guy. So g prime of x is equal to the derivative of the first, which is 1, times the natural log of x, plus the derivative of the natural log of x, which is 1 over x, times x minus 1, which looks like this. So it's going to be kind of a messy looking, complicated sort of fraction-y thing. So here we go. We're looking at the limit as x approaches 1 of my new numerator, 1 minus 1 over x, over my new denominator, natural log of x plus x minus 1 over x. And again, if I put 1 in for all of these things, I'm going to wind up with another indeterminate form. I'm going to end up with 1 minus 1 on the top, which is 0. And on the bottom, I'm going to end up with 0 plus 0 divided by 1, which is 0. That's indeterminate again. Well, what does that mean? That means that I now take the derivative again of f of x. Well, the derivative of 1 is just plain old 0. And remember, negative 1 over x, that's the same thing as x to the negative 1 power. So when I take the derivative of just this part right here, when I take the derivative of that guy, that's negative x to the negative 1. Bring your exponent down, multiply, so negative 1 times negative 1 is positive 1, and then subtract 1. So this is going to be x to the negative 2. That's actually not so bad. Okay? The g of x guy is a little bit more work. So this is f prime again. G prime of x, so g double prime. The derivative of the natural log is 1 over x. And then I've got x minus 1 over x. So I can use the quotient rule, or I can rewrite x to the negative 1 and use product rule. I'm just going to go with low d high minus high, let's see, low d, I didn't even write that right, low low d high, which is 1, minus high d low, which is 1, over low low. So it looks like this. And now I have a new numerator, new denominator. So once again, stepping into my limit. So the limit as x approaches 1 of x to the negative 2 over 1 over x plus x minus x plus 1 over x squared. It's kind of squeezed down there, but here we go. Now when I substitute a 1 in, I'm looking at 1 over 1 squared over 1 over 1 plus, and then x minus, let's see, that should be x minus x plus 1. So I've got a little whoops here. This is getting complicated. X minus x plus 1. So those x's cancel, and I wind up with 1 over 1. So this is going to go all the way down to 1 over 2. Now, it looks really complicated, but the calculus part isn't what's so bad. It's the algebra. The derivative part isn't what's so bad. It's the algebra. You really got to pay attention to your algebra here because there's a lot of places to go wrong. But this is a problem where we can combine a fraction initially so that we can get an indeterminate form to start taking derivatives. Sometimes when you use L'Hopital's rule, or you're looking at some of the different limits where L'Hopital's rule comes into play, you've got to take a natural log or maybe something to the power base of e. It can be really tricky sometimes, especially if you wind up in a situation where you've got 1 to the infinite power, 0 to the 0 power, or infinity to the 0 power. Those are the specific indeterminate forms where you have to do something a little bit different. So here we've got the limit as x approaches infinity of 1 plus 1 over x to infinity. What happens here is if you substitute infinity into this guy, what happens is that whole guy goes to 0. Because the top doesn't change, the bottom gets bigger, your fraction gets smaller, and the result of that is you approach 0. So basically what I've got is 1 plus 0 to the infinite power, or 1 to the infinite power. And since this is what we've got, we're going to have to use a little trick where we take the natural log of the function, which allows us to manipulate the function a little bit and get in there. So let's see what that looks like. If I take the natural, if I let f of x equal 1 plus 1 over x ln, or to the x power, if I take the natural log of that, the natural log of f of x, then this is the natural log of 1 plus 1 over x to the x power. Now, this is an interesting thing because we can actually simplify this by taking the power and moving it into the front of the natural log. So an equality statement would be x times the natural log of 1 plus 1 over x. All right. Now, the only problem with this is it's not in a form where we could use L'Hopital's rule because we don't have a fraction. So I create a fraction with one more equality statement, and this is going to look really weird, but I'm going to take this 1 over x and watch what I do. I'm going to say I've got the natural log of 1 plus 1 over x over 1 over x. Now this looks really, really weird, but here's the thing. If I take the natural log and divide by 1 over x, that's the same thing as multiplying by the reciprocal of 1 over x, which is where I started. But the key from this is, from this guy right here, I can now look at using L'Hopital's rule. I can take the limit as x goes to infinity, and now I can look and see what's going to happen. And what happens is, if I put infinity in both places, I'm going to have the natural log of 1 plus 0 over 0. Well, the natural log of 1 is 0. So when you put all those guys in, you get 0 over 0. That's an indeterminate form. I cannot have it. So I take the derivative of the top and I take the derivative of the bottom. Well, remember that on the bottom we're working with, well, let's just do this. F of x will be equal to the natural log of 1 plus 1 over x. So when you take the derivative of that, Remember, derivative of natural log is 1 over what's inside the log, 1 over 1 plus 1 over x, times the derivative of what's inside the log. Well, the derivative of 0 is 0. The derivative of 1 over x squared, let's just revisit that real quick, or negative 1. The derivative of that is negative x to the negative 2, or negative 1 over x squared. Okay, so what I've got here though is times negative x to the negative 2. Okay, there's my derivative, and we can clean this up a little bit if we want. We can have 1 over x squared times 1 plus 1 over x with my negative sign there, or negative 1 over x squared plus x, because x squared times 1 over x would just be this. Okay, so there's my f prime. G prime, well, if g of x is equal to 1 over x, same thing as this guy. So g prime of x is equal to negative 1 over x squared. Substitute those two different parts in, and let's have a look at what's going on. So my f has become negative 1 over x squared plus x. My g of x has become negative 1 over x squared. Use L'Hopital's rule again and see what happens here. Well, remember that we're going towards infinity, so the way it's written right now doesn't look like it's going to work. But if I have something in the denominator, that would be this guy right here. If I've got something in the denominator, I can multiply by the reciprocal of that. And so my actual problem is going to be negative x squared over 1. Well, we don't want that guy. We want x squared over 1 times x squared plus x. Okay, what we can do from this is factor out an x, because you'll notice that each term has an x in it. So when I do that, I get x over x plus 1. Now when I plug infinity into that, it should work out where I get a 1. So the result of this is when I look at my limit as x goes to infinity, I get all the way over here to 1 right here. And so I come back up and I use this part of my new rule. Okay, so what I'm looking at is the limit then as x approaches a, okay, which in this case is infinity, of e to the natural log of f of x. Okay, well, that happens to be 1. And so the answer for this guy is just going to be E. Now this is a really long problem. There's a lot of steps in it. There's a lot of places to make a little bit of a mistake. It's hard to see that as this limit goes to infinity it's going to be 1, but remember how your horizontal asymptotes work. So once we know the natural log of f of x, once we know that part, we can just substitute it in as the limit right here. Okay, it's a tough problem, and it's one of those problems where you're going to have to practice it a few times. And what I would suggest is work this problem out. You might find a little bit of an easier way somewhere along there to simplify the problem down, but it takes practice to do this. Okay, so there you go. That's using the limit when you have the indeterminate form of 1 to the power of infinity. Okay, what we're going to look at with this next problem, and I've cleared up the slide again, is we've got the limit of x to the x power as x approaches 0 from the right. Now, if you look at this graph, it looks like there should be a limit because the graph has a shape something like this. Okay, and so if we look at the limit of this guy as we get close to 0, like something's going on there. And so what we're going to do is we're going to do this whole natural log business again. And I've got the limit as x approaches 0 from the right of x to the x power, and I'm just going to rewrite it with this whole natural log guy in there. Okay, so now I'm going to look at the limit as x approaches 0 from the right of the natural log of x to the x power. When I do this, I can pull that exponent down in front of the natural log. So let's just deal with just the natural log part. So I've got x times the natural log of x. And again, we want to make sure that we can write this in a way that allows us to use L'Hopital's rule, but we don't have a fraction right now. And so the trick with that is to recognize that the natural log of x divided by 1 over x is equal to x times natural log of x. Just think about it for a minute. When you have a fraction and you're dividing, you multiply by its reciprocal. Okay, so now we can use L'Hopital's rule. So the limit as x approaches 0 from the right of the natural log of x over 1 over x. Now we look and see what's going on with that guy. And what happens is, as we get really close to 0 here, we end up with negative infinity on the top and positive infinity on the bottom. And because that happens, what we have to do is take the derivative of the top and the bottom. So if I let f of x be equal to the natural log of x, then f prime of x is 1 over x. If I let g of x equal x to the negative 1, which is the same thing as 1 over x, then g prime of x is negative x to the negative 2. Okay, another way to look at this one also would be negative 1 over x squared. Okay, those are the same things. So then I use L'Hopital's rule and I check again my limit. So no longer am I using this as my limit, but now I'm going to go, all right, I've got 1 over x divided by negative 1 over x squared. And multiply by the reciprocal here, the reciprocal of negative 1 over x squared. So this is 1 over x times negative x squared over 1. And the x's cancel in this case. And so you end up with the limit as x approaches 0 from the right of negative x, which is 0. So come back up here to this guy, right here. Okay, what are we doing? Well, we've got to now address the whole situation. Okay, we've taken the natural log, we found a limit. So now what we're going to do is we're going to look at the limit as x approaches 0 from the right of e to the natural log of my function, which in this case is 0. And that's going to be the limit, which is going to be 1. E to the 0 power is 1. So there you go. That's all there is to that guy. You know what? Let me rewrite this just a little bit to help us see it a little easier maybe. What if I said e to the natural log of f of x, which is what we just did, which is going to end up giving us e to the 0, which is 1. I know it's a little bit different, it's a little bit strange, but you know, we've worked a couple problems out like this. It's not too bad, so just hang in there, practice them, see if you can do the same exact problem on your own and get the same exact answer. All right, here's the last sort of indeterminate form where we've got to take a natural log, and this time it's the indeterminate form of the limit as x approaches infinity of x to the 1 over x power. Well, this time what you're going to have is, if the top never changes and the bottom does, you're going to have this whole infinity to the 0 power situation. Okay, just think about it. If x continues to grow towards infinity, it's going to be infinity. If 1 over x grows to infinity, it goes to 0. Well, almost anything to the 0 power is 1, but in this case, With infinity, that's not a specific number, so we've got to do a little bit more investigating to find out what to do. Let's go ahead and take the natural log of the function. So we're looking at the limit as x approaches infinity of the natural log of x to the 1 over x power. Okay, so again, just pausing on this for a minute and working with just strictly the natural log of 1 over x, you have x times the natural log of x, which gives us the natural log of x over x. And what's nice about this is we have a fraction set up so we can start using L'Hopital's rule. Remember, if we check infinity on this, we're going to get, this time if we check infinity, the limit as x goes to infinity of the natural log of x over x, what happens is on the top, the natural log continues to grow. Now, it might not look like it on your calculator, but if you punch natural log of x in and you look, it's going to grow towards infinity. On the bottom, x that goes to infinity goes to infinity. So we're left with this guy, which means that we have to take the derivative of the top and bottom, use L'Hopital's rule. And when we do that, the derivative of the natural log then becomes 1 over x. So we like that. Hey, that's pretty easy. And the derivative of x is just 1. So when we do all of this, what we're going to find is when we look at the limit as x approaches infinity of 1 over x, we get 0. So back up here to all of this business, okay? What do? Well, to finish this problem off, you look at the limit as x approaches infinity of e to the natural log of f of x, which we just discovered is going to be 0. So this is e to the 0 power, which is 1. So on this, you just might notice that all these problems got a little bit easier as we went, partially because we became more familiar, and especially on this last one, there was only one time we had to use L'Hopital's rule, and we didn't have to use some weird trick to get there. So there you go. That's a lot of information I've given you from this section over your L'Hopital's rule. There's a ton of different examples. It takes a lot of practice with this to work all these things out. So just be patient. See what you can do on your own. Try them out on your own and see if you can't match some of the answers that I got.